According to Newton's third law, every action has an equal and opposite reaction. So all thrust is just a reaction force created from the gases being ejected out the back of the rocket. So if thrust is a force, we can define it, according to Newton's second law, as the change in momentum over time. Momentum is mass times velocity. So imagine we have a mass m that was at t initial and had a velocity v initial, and now is at time t final with a velocity v final. So the momentum change with time is mv final minus mv initial divided by t final minus t initial. So if m's not changing, this becomes m times delta v over delta t. So the force produced by the engine is m times delta v over delta t. And delta v over delta t is the same thing as acceleration. So F equals ma, which is Newton's second law, which you may have heard before. So we can also rewrite this using derivatives. So force is equal to dmv over dt. In the case of a rocket, v, or the velocity of the exhaust, is fixed, it's constant, because the conditions of the engine and geometry are fixed, so VE does not change with time. So we can rewrite this as force is equal to dm over dt times VE. And dm dt is equal to the mass flow rate, or the change in mass with time. This can also be written as m dot, so we can rewrite this again as F equals m dot VE. But there's an additional effect on the thrust that we need to account for when the pressure of the gases inside the nozzle is not the same as the pressure outside the nozzle. So here we have a nozzle, and inside we have a pressure of the exhaust, PE, and outside we have a pressure of the atmosphere, P0. The difference between these two pressures creates a net pressure on the rocket that actuates on this area, the exit area of the nozzle. This results in a force downward created by the pressures and create a reaction force upwards with the same magnitude that contributes to the thrust. So the total thrust is m dot VE plus PE minus P0 times area of exhaust. Let's say we have a rocket and it's designed so that the pressure of the exhaust, or PE, is equal to the pressure outside in the atmosphere, P0, at sea level. Then at sea level, this term will become 0, and this will not contribute anything to the thrust of the rocket. But once you start going higher up into the atmosphere, P0 starts becoming smaller, and as it gets smaller, the amount this term influences the force will go up. And eventually, once you get into space, all you'll be left with is PE and AE, or the pressure of the exhaust and the area. That's why on the second stages of rockets, they have very, very big nozzles so that they can maximize this area and create the largest amount of thrust possible with this term. So that was the rocket thrust equation, and to check if we did anything wrong, let's do a dimensional analysis. In order for this equation to be true, both terms here needs to be equal to ma. So let's check. M dot is kilograms per second, and VE is meters per second. So this is kilograms times meters per second square, which is kilograms times an acceleration. So this is MA. All good. So let's look at this term. Pressure is newtons over meters squared, and area is just meter squared. Newtons are kilograms times meters per second squared. So we'll just put this over meters squared and multiply by meters squared. These two cancel, and we're left with kilograms meters per second squared, which is the same as what we got on this side. Kilograms times an acceleration, mass times A times acceleration, all good. So now let's simplify this equation into something a little more easy to manage, which we'll use when we're going to derive the rocket equation in a later video. We'll want to write this as m dot times a v equivalent, which just encompasses all of this. And v equivalent is just equal to VE plus PE minus P0 times AE divided by m dot. So when you multiply the equivalent by m dot, the m dots cancel, and this is equal to this.